Yes. Okay, excellent. Hello and welcome to our Spotlight session. My name is El-Sharif and I am a stream owner at ACE. ACE is a community of machine learning researchers and practitioners who have gathered around topics on AI research, engineering, and products. We host weekly live sessions like this, and we also produce premium content on various subject areas. We have 14 different streams focused on various machine learning topics. This particular stream is focused on machine learning interpretability. Today, we will be hosting Muhammad Rehman Zafar. He goes by Rehman, and he is a PhD candidate at Ryerson University. His research is focused on creating interpretable models by combining interactive visualization and machine learning to help end users better understand machine learning decisions. Rehman is also a software developer and has successfully deployed many machine learning solutions in production. So he is both a scholar and a practitioner. Today, Rehman will be presenting his paper, DLIME, a deterministic, local, interpretable, model-agnostic explanation approach for computer-aided diagnostic systems. The paper was presented in the 2019 ACM KDD conference workshop for Explainable AI for accountability, fairness, and transparency. And we want this to be an interactive session and encourage you to participate and ask questions through chat during the session. We will also have questions at the end of the session, so you can ask during the session or wait until the very end. I'm going to start before I turn this over to Rehman, and I'll start with an example to highlight why this work that we're reviewing today is important. And what I'm showing you here is a visual example cited in the literature where the researchers had a task of having a machine learning algorithm predict healthcare outcome based on X-ray images of the lungs. And what you're seeing here on the picture on the left side of the screen, where there's a red region, this is a heat map indicating where the machine learning algorithm was focused in trying to make its prediction on healthcare outcome. And what it was focused on was a metallic piece at the corner of the image, and it was not even looking at the lungs. And certainly that insight indicated that that machine learning algorithm trained to noise or trained to something that was not intended. The image on the right, it's maybe hard a bit to see, but when we share the slides, you can see them. Has the word portable. And the word portable here indicated the type of X-ray unit that was used in basically creating that X-ray image. And there were three types of X-ray machines that essentially were used as proxies. Portable machines identified patients that were not mobile and had to have the X-ray come to them. There was another type of X-ray machine which basically identified which patients walked into an emergency room, and then there were inpatient units that people were scheduled to come in and get these X-ray images. And what essentially occurred here is that the machine learning algorithm cheated. It did not even look at the lungs and used these background text to decide or to predict the healthcare outcome. This is basically a quick example identifying why it's important to understand why machine learning algorithms are coming up with the prediction. Next, I want to share with you a method called DLIME, which Rehman's paper is based on. So if we can go to the next slide. DLIME stands for Local Interpretable Model-Agnostic Explanation. And what we're showing on this particular slide is the fact that this paper came out in 2016, and it nearly has 3,000 citations. So you can hardly have any research paper right now on machine learning, interpretability, or explainable AI without some mention of LIME. And Rehman's work is really interesting because he came up with a way to improve on this very popular method of interpreting machine learning algorithms. With that context and background, I will turn it over to Rehman to present his interesting work. Rehman, the floor is yours, sir.
Thank you, Ali, for your for the introduction. So I will start with the roadmap. So first, I will go through introduction and design models of our XAI. Then I will discuss methodology and results presented in DLIME paper, and then I will conclude the presentation. So artificial intelligence and machine learning has emerged in sensitive domains such as medical, and state of the art shows that ML algorithms are powerful in terms of predictions. So however, they have certain limitations. As you can see in this picture, it takes an input and then performs some kind of computation, and it shows results. So it does not provide any kind of insights why this model is reaching to a particular decision. That's why we need explainable models that can explain actually the inner working or some kind of insight, and provide some kind of insights that can be able to understand decisions in a good way. So therefore, we need explainable AI models. So usually, machine learning models are dense and difficult for end users to understand. Therefore, XAI models are required. Here, there is no globally agreed upon definition for XAI. Many authors use these terms in an alternative way. For example, some are using explainability, some are using interpretability, and in two papers like Tomset et al. And Lipton, they both of these authors defined these terms in their own way. So they defined explainability as the extent of clarification provided by the system about its decision and the reason behind this decision. And they are defining interpretability as the amount of information a user is simulated from the transparency and the relevant explanation to use it effectively. So in most of the papers, you will find these terms interchangeably. So here we focused on interpretability and like the amount of information a user is capturing or routing from the explainable models. So Ali already presented a motivation, so I will give you further. I will add further motivations here. So one is like GDPR. So GDPR is a General Data Protection Regulation, where they defined if someone is using AI algorithms, then if end user asks the reason about the decision, then your algorithm must have to be capable to provide insights or provide explanations. So here AI is acting as a third party between patient and physician relationship. So if a physician is using our AI algorithm, so he will be the solely responsible for all decisions and its outcome. So before using this AI in healthcare, that algorithms must be validated with the available data sets, and it should be working with real data, not on synthetic data. Why explanations in healthcare? For example, if someone is visiting to a physician and physician says you have this certain certain disease and you need a surgery, then you must ask. Definitely, you are going to ask what is the reason, what type of this surgery is, how you come up with this decision. So as shown in this picture, when a physician gave a visit to a physician. When a patient gave a visit to a physician, so doctor responded, "Are you well? The computer shows me that you are fine, and it has given me 100 reasons for it." But patient now asking, "Doctor, are you sure that I am okay now? My head still hurts." Machine learning algorithm is saying patient is okay, but actually he is feeling hurt again. So that means there it should provide some authentic reason why this is happening, why machine learning algorithm saying you are fine, right? So in terms of healthcare, it is also important because its consequences can be far-reaching, like someone can die with the wrong decision. So that's why explainable models are more important in healthcare. So these are the design models. So these design model can be divided into many groups. We can divide in local and global, transparent and post hoc, and model specific, model generic. So we can actually divide these models into various groups. So here I'm talking about two categories, which is one is transparent and the other one is post hoc. So transparent means you have to provide you have to reveal all the information that model is using, how model is actually working. So you have to provide all that information. You have to make a transparent model. And in post hoc explanations, you are not interested in that internal mechanism. You are just interested in explanations, how this model is generating these kind of decisions, why it is reaching to a certain decision. So you are only interested in decision, not in the mechanism of the model. So that's why it is called post hoc. So post hoc explanation explains why a black box model behaves that way, right? So the other thing is outcome explainable model. So you can group into two things. One is local and one is global. Local models takes one instance at a time. It performs some computation and come up with certain explanations that may be a rule, that may be a qualitative information, whatever. So they can provide you that outcome. So here local interpret models are not working on a complete data set. They are only working on a certain instance. Maybe they are accepting one instance as an input and performing some computation and giving you output. While global models provide an interpretable model able to mimic the overall logic or behavior of the black box and to explain its logic. So it takes complete data set, performs some computation, and then it will come up with the predictions that can represent a complete data set, not in local regions. So I will explain what I mean by local explanations in next slides. A model agnostic versus model specific. So here these are two models. In first diagram, it is all modules are independent to each other. So you can change a specific module and you can come up with different algorithm, or you can change, you can improve the results of previous models. But in model specific, all modules are dependent to each other. You cannot modify a single module. So here, if you can see, a red line represents black box and interpretable learner. So both modules are totally independent. So if you are changing your interpretable model, it is not affecting to others. For example, you can interpret random forest neural networks with same model. But if you are talking about model specific, maybe it is particularly designed for trees like random forest. So there is an example, there is a method called tree interpreter. So tree interpreter is particularly designed for model specific decision trees. So that is a model specific approach. So here these are design models for explainable artificial intelligence. So this is the LIME. I will explain how LIME works. So here, if you see this picture on the right side with blue background, you have different dimensions of data set. And each data point is representing a test point. And the regions, like there are two different colors. One is blue and one is like pink. So both colors are different and representing different clusters of these data points. So there are many clusters there. It is a hyperdimensional data set, and the plus sign is representing the interested point of interest, and the line, the dashed line, represents the separate boundary of the separating boundary of these two clusters, like circles and plus sign, and then the line between is representing is linearly separating these clusters. So on the left side, if we are talking about one cluster, and if the data is well separated and clusters are easily identifiable, then single line can work, and we can use linear models to separate these things. If data is linearly separable, linear model will works, and if the data is not linear, it is hyperdimensional, then you have to perform some kind of task in which you can define explanations, you can generate explanations, and you can differentiate between different clusters. So here, what LIME does, it takes one test instance at a time, then it perturbs the data around that the test point, and it generates around 5,000 samples around that data point, and perform generate some train some model and compute some weights, and then it uses those weights to train that interpretable model and to extract the features, right? So here, what it can do, for one instance, it can generate multiple explanations. For example, because it is generating synthetic data. So synthetic data is based on random perturbation. So when it is using random, it is generating synthetic data randomly. So data set is going to change each and every time when you will execute this algorithm. So therefore, each time it will give you different explanation for different for the same instance. So that is instability. That is defined as so this issue is defined as explanation level uncertainty, and it should be handled. So because
so Rehman, we have a couple of questions that I maybe just want to interject here. So the first question that came in from the audience is, how is local interpretability better than global? Is it better? And if it is, why?
We can't say local is better than global. So local is easily to achieve. So it is hard to explain a model globally. So that's why if the data is not linearly separable, then you have to divide that data into some subspaces, and then on those subspaces, if those are separable, then you can use a linear model or a simple model to generate some explanations.
So in your example, the explanation of separating the red cross from the blue dot, if that dot was placed somewhere else in the space, we would come up with a different explanation and a different reason why that prediction took place.
Yes.
And then stability, when we're basically saying stability is an important concept here, is it how in this context is stability defined? Is it in terms of the predicting features that are used to generate the prediction? How is can you maybe just elaborate a bit more on the concept of stability that you've highlighted?
Yeah, actually stability means when you will execute LIME multiple times, so for the same instance, for the same data points, it will give you different feature set.
Okay, so I run LIME 10 times, and the first time I run it, I got one explanation and just saying these are the 10 features that I used. I run it the second time, I got possibly a different set of features. So that explanation that I'm getting, I cannot trust.
Yes, that's true.
Okay.
So this kind of uncertainty is known as explanation level uncertainty. That should be handled.
Okay. Now, does LIME give you a confidence in the prediction? It says, my confidence level in this prediction and the reasons that I gave you is this, or is that not provided?
If someone that is aware of that data, so he must know these attributes are important in this prediction. These features should be important. right? So he can define, by looking at those explanations, he can see, okay, so it is because of this, because of this, because of this attribute, so it is reaching to this decision. So it will give him an idea, give them an idea that these features are important, so we need to look into these features more carefully. So maybe they can look on into other features as well. So why LIME is not picking other features, right? So that is the idea. So it is actually getting important features that can be useful to explain a certain cluster, a certain subspace.
Yeah, thank you. Appreciate. Please continue.
All right. So here our focus is to like address a question. We are addressing this uncertainty, explanation level, and uncertainty in at a more granular level. So the basic answer we want to answer we want to answer question we want to answer is, can explanations generated by locally interpretable models provide consistent explanations, consistent results for the same instance? So that was our basic question that we want to answer. So here we proposed a DLIME. So it is based on LIME, and the only highlighted part is different from LIME. So instead of creating synthetic data, we are using hierarchical clustering to group create subspaces. We are not generating synthetic data. We are only using original data, and then we are grouping it into subspaces using hierarchical clustering. And then we take one instance, test instance, and we use KNN to predict the subspace of that data instance. And then we will use that subspace for further processing to get weights, to train interpretable model, to get features. We will use those original data points based on those clusters.
Now, when coming up with hierarchical clustering, do you need to establish any parameters in advance, or establish the size of these clusters in advance, or that's not the case in the solution you developed?
No, in hierarchical clustering, you don't need to provide any kind of parameter like how many clusters you need. You don't need to provide that. It does not require pre-knowledge.
Okay, thank you.
Yeah, so it will give you a hierarchy of those data points, and then you can represent in using dendrogram, and then you can see how well this data set is separated, how many subspaces are in that data set, and then you can cut with a certain distance, with a certain threshold, you can cut those clusters into multiple subspaces. So here, this is the algorithm of DLIME. These are the simple steps. It clusters the original data using hierarchical clustering. Then we use KNN to find the subspace which is related to relevant to that test point. Then complex model, we use complex model to predict the outcome of the cluster. Fit a linear model or simple model to select cluster, then select features from M features using one of the feature selection technique that best describing the complex model outcome from the cluster. Then extract those weights, extract the weights of those features and display to the users. So these are the explanations.
So in your case, when these feature selection techniques, you guys used the default LIME techniques. You did not alter that in any way?
No.
Okay. So the main part that you guys changed was coming up, it's essentially step 1 through 4, right?
Yes.
Okay. Okay, thank you. Thank you.
Yeah. We use these 3 data sets to compute the results. So the first data set we used from UCI repository was breast cancer. It consists of 569 observations and 30 features. And the second data set we used for liver patients, it consists of 583 observations and 11 features. Hepatitis patients data set, It consists of 155 observations and 20 features. So these three datasets we use to compute our results.
And these are all tabular datasets, correct?
Yes, these are all tabular datasets. Actually, breast cancer dataset was in the form of images, but some authors extracted some features and uploaded at UCI. So we use those features.
Okay. Now, just curious, your approach would work with, because LIME works with text or images as well, the approach you described is not specific to tabular datasets. It could apply to those other data formats as well?
Yes, but we did not apply on text or images yet. So we just worked on tabular data. So yeah, it can be applied onto images and text data as well.
Okay, thank you.
So the first table shows breast cancer dataset. So it looks like this. So it has two classes, benign and malignant.
Yeah, sorry for the interruption, Rehman, and apologize to everybody else on the session. But we are back online right now, and we are picking up from where we left. So, Rehman, the floor is yours, sir.
All right. So breast cancer dataset looks like this. So it is a tabular data. It has two classes, and it has values in tabular form. So here we used hierarchical clustering, and this picture, this diagram shows. This diagram shows a dendrogram, and we are actually cutting this dendrogram on the largest distance, so it will give us two clusters. So each time, if the dataset is binary, most probably it is going to give you two clusters. But in cases, in hyperdimensional cases, it is going to give you different subspaces, and then you will look into it in how many subspaces you want to cut your data. So
it's almost like the entropy of a decision tree, where it's figuring out the maximum the value that's going to separate the data in the maximum way. Is that a reasonable analogy to make?
Yeah, that's what we did in this paper. So we just cut this dendrogram on the largest instance.
Now, is it would we know which? Just like when you're examining a decision tree, would you know which variable was used and which value was used to cut off at the top layer, the second layer, just like you would in a decision tree, or that's not easily determined from this diagram?
It's not like decision tree. Based on distance, using a Euclidean distance formula, it is computing distance between data points. So based on that, it is just based on those distances, it is computing these data points. Okay. When we are taking one instance that we need to explain, then we use K-Nearest clusters to find the closest subspace to that test instance. After taking that subspace, we are performing future computations. So these are the evaluation metrics that we use. One is the Jaccard similarity. So here, the purpose of using Jaccard similarity is actually we want to look in how many attributes are in common when we are executing these algorithms 10 times. So iteration in each execution, how many attributes were same for the same instance, and how many instance were different. So that's why we use Jaccard similarity to just find out the common attributes. And J distance is the actually 1 minus whatever the Jaccard similarity is. So it will give you the distance between two or more attributes. So this diagram, actually for this diagram, we used neural networks as a black box model, and we used DLIME to generate explanations. So here on left side, vertical line, we are showing DLIME, results of DLIME, and on right side, we are showing the results of LIME. And on horizontal rows, we are showing iterations. We computed these results on 10 iterations, but in this diagram, I only showed 2 iterations. In iteration 1, you can see LIME generated some attributes which are totally different to LIME. And here in iteration 2, if you see both diagrams, on left side has same attributes and same weights, but on the right side, each attribute, we have different attributes and different weights. So here you can see yellow highlighted attributes are different in both iterations. So that is the uncertainty. So these results are not consistent. But if you look at DLIME, so these results are consistent. So here, what red lines and what green bars mean. So here, red bars actually giving you negative coefficients of linear model, because we are using linear model to generate explanations. So here, red bars are the negative coefficients, and green bars are the positive coefficients of that linear model, right? So here, similarly in LIME, so they are using same thing. Negative points represents red bars, represented with red bars, and the positive coefficients represented with green bars. So these are the only two iterations for this. We computed this result on 10 iterations. After executing 10 times, we see we actually use this diagram to display the distance between these attributions. So on left side, it represents DLIME. So DLIME has 0 distance. So it means every time it generated same explanation for same instance. But on the right side, you can see uncertainty in LIME explanations. So these are results, we presented these results after 10 iterations. So this is the complete execution results. So on breast cancer dataset, we used 2 black box models. One was random forest and one was neural network. So we used both models as a black box. And in case of DLIME, every model is actually generating same explanations. But in case of LIME, you have you have a significant amount of difference. So in case of random forest, you have 9.43 distance, and in case of neural network, you have 57% distance. So it is a huge difference. So you cannot only trust what LIME says. So you have to be consistent. For at least for same instance, you have to generate same explanations. If you are generating different explanations for same instance, then that means something is wrong with that model. So that was the limitation of LIME. So that we answered in this DLIME. And now I'm concluding my results. So my presentation, experimental result shows the superiority of DLIME, where we quantitatively determine the stability of DLIME compared to LIME using Jaccard similarity among multiple generated explanations. So here, since DLIME is totally depending on clusters, so if the quality of clusters may affect the quality of explanations and accuracy and low in prediction as well.
So Rehman, we have a quick question from the audience.
Yeah.
Basically, it's going back to your main point is DLIME is stable because it's using clustering, which is done on the training data. So can you just respond to that question, please?
Yes, actually, clustering is done on training data. Yeah, training is done on training data. And then we are using one test instance. We are picking one instance from a test data, and then we are finding its closest subspace.
So you're superimposing those or imposing those clusters on the test data. You're not relearning the clusters every time. The clusters, you've learned them at training time, and then you just use those predefined clusters during tests. Is it part of the model, if you will?
Yes.
Okay.
So instead of generating synthetic data, we are using these clusters that we actually got after applying on training data.
Okay. Thank you, Rehman. Any other comments or questions from the audience? Now is the time. Okay. And so just gonna ask a couple more questions here. Okay, but go ahead, speak to this the slide, and we'll just go ahead and ask you a few more questions.
All right. So our resources are available online. So you can find paper on our archive directory. And here I have pasted a link in this slide. And then you can find the complete code from my GitHub repository. And you can use this link and you can use barcode to get there. So you can download and experiment with that. Thank you for the...
So a few more questions that are just coming through here.
Yeah.
Now, you applied DLIME to medical data sets. Is there anything specific about your approach to medical data sets, or would we be able to apply this to any tabular data sets, financial data set, etc.?
Yeah, it can be applied on any data set, but our main focus, main application is medical. So that's why we are using medical data sets.
Okay.
Yeah.
Now, another question here is, you tackled the lack of stability or the stability issue of LIME. The other common metric that's used in post hoc methods is fidelity, or the explanation fidelity to the ground truth.
Yeah.
Is there any impact that DLIME has on fidelity? I know you're making a claim on stability, but what about fidelity?
Fidelity is the same as LIME, so we did not change that. We are using same equation.
Okay, so it always it comes up with the same prediction as LIME, but it just provides different reasons for that prediction.
Exactly. Yeah.
Okay. Now, you also use the Jaccard coefficient to measure stability. There were other available options, potentially like the cosine similarity, the Pearson correlation coefficient. Why is the Jaccard coefficient the most appropriate method that you chose for measuring stability?
Actually, for other approaches like cosine similarity, we may need TF-IDF to compute their frequency and inverse document frequency that we will use to compare vectors. But in Jaccard similarity, we are just finding common attributes among all attributes. So that's why we use this Jaccard similarity because of its simplicity, and it was fulfilling our purpose.
Okay, and this is a fun one. What's next for you guys? What are you planning to do next to extend the work that you did with DLIME, which definitely is showing a lot of interesting and promising results? Where are you going to take this, and what are you going to do next?
Okay, as you can see in this slide, DLIME and LIME is generating different explanations, and we don't know which explanations are good and which explanations are bad. So we cannot determine those. So our next focus is to determine these. We need to quantitatively identify which explanations are correct and which are not.
So how does that look like? Are you like potentially bringing subject matter experts and asking them to rate these explanations? How are you determining the goodness of the explanation, if you will?
Yeah, a human should also involve in this decision, but we are working on quantitative side. We are not working on qualitative side. Our main focus is quantitative side. So how we can quantitatively identify these explanations.
Okay. Okay. More to come, I suppose. Well, we are about to wrap up here, so I'm just going to give the audience a last opportunity if they want to ask additional questions. We will be posting the slides on our website. I encourage you all to go to ai.science to visit our website and to get access to the slides if you would like. And this is a really interesting work, Rehman, that's made a contribution on stability for a very popular method, LIME. And definitely this is something that has a lot of potential to be useful and has a lot of opportunities for to be applied in the medical domain and other domains as well. With that, I will conclude our session, and I thank everybody for attending, and we hope to see you in a future session soon. Thank you very much, and we will conclude our talk today.
Thank you, Ali, for the opportunity.